Okay, in this problem we have a ball that's attached to a rope. The ball is moving with an initial velocity of VA, and VA is given to be 4 feet per second. The rope is being pulled down with a velocity VC, and VC is 6 feet per second. And we're asked to figure out what the velocity of the ball is when this radius right here, let's call this point B, is equal to zero point 0.6 feet. So let's first look at a top-down view. Maybe you'll make what the question is asking more clear. So if this is a table with a hole in it, it has a string that is connected to this ball. And the ball is moving with the initial velocity VA. Now, as the ball is being moved, since the string is being pulled down at 6 feet per second, the path that the ball is going to take is sort of going to spiral into the middle. So it's going to sort of look like this. Sort of something like that. And we don't know exactly where this 0.6 feet radius is, but let's just say it's right here, and this is point B. So at this point B, what's going on? Well, at point B, we have the ball, and the ball is going to have a force from the string. So this is going to be its tension force, and it's going to have two components of velocity. It's going to have some component of velocity from its velocity, this VA. So its velocity, we'll call it VB, is going to be somewhere along like this, tangential to its path, and it's also going to have a velocity C, which is pulling it towards the middle of the table, and this is the velocity C. So the magnitude of its velocity is going to be right here, and we just need to figure out what this VB is right here. We know what VC is. VC is this constant 6 feet per second. So we just need to figure out VB, and then we can figure out what this final velocity is equal to. So one equation we have to deal with something like this is a final angular momentum is equal to an initial angular momentum plus the sum of all the impulses and moments that the system has. And in our case, the sum of the moments is going to be equal to 0, because this tension string T is always going to pass through this z-axis right here. And this is what the ball is rotating about. So it doesn't have any impulses, it doesn't have any moments, and we are just left with the equation that the final angular momentum is equal to an initial angular momentum. And we know that angular momentum is equal to mass. Well, put this over here. Angular momentum is equal to a mass times a velocity times a perpendicular distance. In our case, this perpendicular distance right here is going to be r1 or r2. So if we look at this equation, we have our mass at this second point. So mass at B is equal to a velocity of B times this R2 in R, and let's just call this R2 R of B, just to sort of stay consistent. So R of B is equal to the initial angular momentum, which is going to be this mass at A times the velocity of A times RA. And again, let's just call this what we had R1, RA, just to make it sort of consistent with the notation we're using in this equation. Should have probably thought ahead a little bit more. But we know that the weight of this ball at the second point B is going to be this 0.8 pounds divided by gravity. And gravity is 32.2 feet per second squared. And the velocity of B is what we're looking for. And the radius of B, we want to know what the velocity is when the radius is equal to 0.6 feet. So it's equal to the mass of A, which is 0.8 over gravity. The mass doesn't change. And we know the velocity of A. The velocity of A is 4 feet per second. And we know the radius of A. The radius of A is 1.75 feet per second. So if we solve this equation, this actually cancels out because it doesn't change. We get the velocity of B is equal to 11.67 feet per second. And that's this component right here. So in order to solve for what our velocity is, our final velocity, we get the final velocity is just going to be the magnitude of VB squared plus VC squared. And this velocity is going to be equal to the square root of 11.67 squared plus 6 squared. And this is equal to a final velocity of 13.1 feet per second.